Okay, welcome to 1014 and 618. Today we're going to be talking just a little bit more about topic modeling. I just want to kind of wrap up with a picture of some of the sort of models that kind of go beyond just the standard LBA and that we looked at last time. And then we're going to move into variational inference. And so let's see. Yeah, kind of a fun new approach to approximate inference. Okay, so homework 4 was out last week and is due on this upcoming Monday, so a week from today. And I think our hope was, again, that homework 4 we kind of defined in such a way that that it should be a challenging assignment, but not excessively challenging, but I think as well, maybe the key point that I want to make here is just that what we really set out to do with this homework was to kind of expose you to modern techniques, right? So one of the things that we had sort of considered doing here was just asking you to implement sort of a vanilla LBA, and we think that this sort of more modern model is actually just sort of a better use of your time. Okay, so let's talk about some extensions of LDA. So there's this wide variety of models. Once you kind of have this framework in place, this notion of being able to write down a Bayesian network that describes a generative story for where these documents and these topics came from. And you can start to sort of build up a repertoire of similar looking models that try to capture different things. So one of those is called correlated topic models. And they're correlated in that there's actually a different prior placed over the actual topic assignments, such that you can actually get something sort of more interesting than just sort of the standard multinomial distribution over topic assignments. So a dynamic topic model is really fun. We'll look at this, I think, in a little more detail, because it can actually learn topic change over time. So there's actually a notion of sort of groups of documents, right? So here's group 1, here's group 2, here's group 3, and each group might be a set of documents from a different decade. And maybe you have 10 decades worth of data. And so you can actually see how the topics are changing over time. And then polylingual topic models are useful, say, if you have something like Wikipedia, where for each document you have maybe not exact translations of the document, but you have sort of comparable versions of a Wikipedia page, right? If you go to the English and Spanish Wikipedia pages for a particular topic, they're not going to be identical. They're written by completely different groups of authors, but they tend to correlate in terms of the actual contents. And so you can start to build up representations of topics that are actually in a shared vocabulary across multiple different languages, say T different languages. Okay, so so the correlated topic model is kind of about rejecting the Dirichlet prior, and the Dirichlet is a great distribution. It gives you a distribution on the simplex, which is the space of vectors that sum to 1, right? Or probability vectors, right? So vectors that sum to 1, whose entries are non-negative. And basically it kind of assumes that the components are mostly independent. But if you think about real data, an article talking about fossil fuels is more likely to also be about geology than about genetics. So there's some notion that when you have a distribution over topics that is describing a particular document, certain topics are more likely to correlate than others. And so the logistic normal is also a distribution on the simplex, but it can actually model dependence between components, right? So if you look at these distributions from the Dirichlet, they tend to be, you can kind of move the center of probability mass around, but it's somewhat symmetric as a prior. By contrast, the logistic normal is actually able to give you these kind of skewed priors, and so then you can actually use this as a prior over those document level distributions over topics. Okay. And so essentially all we're doing is replacing this one little bit of LDA, which used to be a Dirichlet prior, with a logistic normal prior. Okay, so this does provide a better fit to text data, but the whole reason that we were using the Dirichlet prior in the first place was because of Dirichlet multinomial conjugacy. And so once you switch to this logistic normal prior, now you have to do something a little fancier in terms of inference to actually work with this model. Okay, but why would you care to do this? Because at the end, you could actually visualize your topics and how they are actually correlated with each other. So this particular picture is connecting up the top words for each of the topics to the other topics that were sort of most highly correlated according to the prior. And so, so I don't know if we can find fossil fuels on here, but this is the one that seems to be about genetics, genetic population, populations, difference, and variance. And you can see that the topics that it's connected to, like this one here, also kind of appear to be about similar things. So this is about like sequences and genome and DNA sequencing. And there are entirely other separate subsections of topics, like this one over here, that's kind of completely disconnected, right? United States, women in the universities, students in education, science, scientists, etc. These are all kind of in their own little cluster of topics. And so this is a different way then of visualizing the actual contents of some really large corpus. Okay, so so I should add here that the examples that I'm showing are going to tend to be these examples on text corpora. But people have applied these sorts of models all over the place to computational biology problems and computational neuroscience problems, computer vision problems, where the notion of words and topics changes depending on the actual application. But we still can kind of refer to them as topic models. Okay, so the dynamic topic model, the high-level idea is, you divide the documents up by year, as I had mentioned, and then, this is the interesting part, you add a dependence of each year on the previous one. So this beta, this is the parameters of some Dirichlet distribution. The beta here are the actual parameters of the topics themselves. And so what we're doing by connecting beta k1 to beta k2 is actually saying that the topics in 1 year are actually going to be similar to the topics in the previous year. And so what that allows you to do then is look at how a topic changes over time. And so you can see here in 1880, so this was the documents from 1880 that gave rise to this topic, had words like electric, machine, power, engine, steam, tube, machines, iron, battery, wire. And then as time goes on, this topic appears to kind of change. And so gradually we can see, like, by the 1950s, that same topic is now talking about tube, apparatus, glass, air, chamber, instrument, small laboratory pressure, rubber. And then finally by 2000, we have devices, device, materials, current, gate, high, light, silicon, material, technology. It starts to sound like, so this technology topic kind of was drifting from sort of a very different use of engineering in the early 1900s to something like maybe computer chip development. As well, you can also look at the prevalence of topics over time, and you can also look at the prevalence of sort of word frequency over time. And so, so here we're looking at basically two separate topics. So these titles here, we should be careful to observe that those titles for topics are kind of retroactively applied, right? So there was some collection of words, some distribution over words that the authors of this paper thought kind of looked like a theoretical physics topic. And then there was another one that kind of looked like a neuroscience topic. And so in neuroscience, you know, in the early 1900s, you know, nerve was kind of one of the most prevalent words for that topic, and then gradually neuron took over. And for theoretical physics, people were concerned with forces, you know, back in the 1880s, and then lasers in kind of the late 1900s. And there was kind of this interesting trend towards discussion of relativity in the middle. So what's fascinating about this is that, you know, just by looking at this plot, you know, we kind of like all see these words, these distributions over words, and we can all just kind of like nod along. Because what they're capturing is something that's kind of admittedly cherry-picked, but very intuitive about what's going on in these documents. And so the hope is that something that might not have been intuitive to you about what's going on in the documents might jump out by being able to examine them in this way. Okay, so polylingual topic models, you can similarly kind of learn that, you know, there might be some topic like this one, and the same topic is reused across 12 different languages, learned on Wikipedia, and so you know, all of these tend to be hopefully about space travel. Okay, so this is another topic that tends to be about Spain or Spanish. One about poetry. Okay, so so the point then is just that that we can kind of begin to also look at the proportion of tokens assigned to a specific topic, and ask the question, you know, which topics are sort of more or less prominent in the corpus, right? So this particular topic, world, ski, kilometers, and one, appears mostly in languages spoken in Nordic countries, and Ottoman Empire, Khan, and Byzantine is appearing mostly in countries with languages, mostly in languages spoken in countries near Istanbul. And then there's other topics like this one about TV and movies that's maybe uniform across countries. Okay. So a lot of times you also have actual labels or sort of some observed metadata about what you'd like to model. And so supervised LDA provides an opportunity for you to include in the generative story both where your words came from, but also where that metadata came from as some observed variable. And then the model that you're looking at now says, well, you know, we've spent a lot of time recently thinking about ways of representing our data, be it words or images, or data about cancer cells in low-dimensional vector representations. And so one sort of key idea is to generate, instead of words as sort of these discrete entities, to generate a vector representation of each word. And so this is exactly like LDA, except that now instead of generating words from a multinomial distribution, the roll of a die, we're generating an entire vector from some multidimensional Gaussian. Okay. And what's fun about this, though we opted not to ask you to actually make this visualization on the homework, is that you could plot these actual word representations in some low-dimensional space, say by running PCA on the actual word vectors. We did remove this question, right?
Yes.
Yeah, okay. So, yeah, this just seemed like it would be really cool, but maybe not like the best use of your time. So, whoops. So, what's being done in this figure is each of the words was some high-dimensional, some 100-dimensional vector, like what you're working with. And then they ran PCA on both the word vectors, but also the topic vectors, and brought everything down to just 2 dimensions so that they could plot them. And then what they did was they plotted the first 2 principal components for the word embeddings of only the top words in some topics, right? So they didn't show every single word, but just sort of the most prominent ones. And then they also have the actual word color coded according to the actual topic for where the word appeared in like the top 10 list for that topic. And so what we can see is just that you kind of get these clusters of word vectors appearing in topics in sort of a reasonable correlated way. Okay, so topic modeling broadly is allowing us to do this really powerful analysis in an unsupervised way of large data sets. And fundamentally, LDA is sort of providing us with this really framework for describing a way of generating data that can be extended in all of these interesting ways. And approximate inference is really what enables all of this to work. Because at the end of the day, everything that we just did here, both learning as well as coming away with the actual topics themselves, was cast as an inference problem. And so it was that sort of boiling down of learning to inference and combining marginalization over latent variables and also estimation of parameters simultaneously that allowed us to think about Bayesian inference and learning. Okay, so a good question to ask yourself is, this all sounds great, but what if we don't actually know the number of topics ahead of time? And so there are actually good solutions here, and one of them is Bayesian nonparametrics. And the idea is that we can actually replace something like a Dirichlet prior over a finite number of k topics with what's called a Dirichlet process, which would give us a distribution over infinitely many topics. And the sort of interesting part about Bayesian nonparametrics is that we can work conceptually with an infinite number of topics, and yet we can boil the computation down to something that fits in finite space, so that we can actually work with it on a computer. So there's sort of a wide variety of other modeling constructs that come out of this space. Okay. Yeah.
Why is it called nonparametrics? What's the...
Oh, great question. So, so this is probably a good moment to mention. So this topic, right now it's not on the schedule, but it might spontaneously appear on the schedule because of some like scheduling constraints that I have, where I might spontaneously disappear for a lecture. And so I've actually got a pre-recorded lecture on this that I'm not releasing unless we need it. But it's something that I could release later if you guys are interested in the topic, just as kind of an introduction to the space. But basically, the short version is that there are a lot of models that we call nonparametric because so a parametric model has a finite number of models, and the number of parameters is defined independently of the actual data itself. So a non-parametric model, it's not that it actually does not have parameters. It does have parameters. Like there's actual topic parameters. It's just that the number of parameters that we end up working with is actually a function of the data itself. So these models, I think it would have been better for everyone if they had been called sort of infinite dimensional or something like that. But yeah, there are certain kinds of models that we can work with that truly have no parameters, but these particular kinds actually do. Okay. So this is sort of an advanced topic that we won't go into today. So broadly, approximate inference is sort of opening up all of these different ways of doing things for us, right? So we started out with these exact inference methods that were sort of specifically catered to solve what we were calling the inference problems at the time. They were map inference, computing marginals, and estimating the partition function. And we've broadened that with Bayesian inference to say, well, really learning parameters can also be an inference problem. And the approximate inference method that we've now spent a lot of time on, Markov chain Monte Carlo, is one solution to that problem. But we're going to move to talking about other solutions like variational inference, where we can recast this entire problem in a different light, like in a light that is not based on sampling. Okay, so I want to begin with just a high-level look at what variational inference is doing, and how it differs from Markov chain Monte Carlo methods. Okay, so the problem setup that we're going to be working with today is a really general one, and I want to make sure that it's abundantly clear just how general this problem setup is. So here's one example of the problem. Okay, for inputs x and outputs z, we want to estimate the posterior p of z given x, because that posterior is intractable. So we can't. So this is like the problem that you were solving on homework 2, right? You have some conditional distribution over, say, output variables, in some factor graph, and you want to estimate the, say, marginal probabilities or some distribution over those variables. Now, in homework 2, we purposefully chose this factor graph that was tree structured, right? Everything about it was chosen so that while you were working with it, you could do regular belief propagation and compute the distribution exactly. Okay, the whole time that we were doing that homework assignment though, all I was doing was thinking, gosh, this is such a terrible model. Okay, I knew that we had to do that model because it was a tree and it made everything kind of clean and nice for the homework. Pedagogically, it was the right thing to do. But deep down, I just felt like, I'm crippling all of you by making you work with this model, because I know that part of speech tags, which are the leaves of the model that you were working with, they actually have sort of this temporal left to right dependence. And so ever so desperately, I wanted to add extra factors in here that connected them up in a chain. Okay, but I couldn't do that in homework 2 because we had to have exact inference and make everything simple. Okay. So if we had that factor graph, which would have made much more sense for the data that you were working with, suddenly this posterior distribution, P of z given x, would have been intractable. Okay, that's problem number one. Problem number two here is suppose x is all of your training data. Okay, in the first problem, we're assuming x is something like one sentence and z are the variables for that sentence. In problem number two, I'm saying let x be your entire training data set. Think like LDA, okay? And z is now the parameters of the model, okay? And maybe parameters here we could actually use loosely to say, maybe it's not just parameters, maybe it's parameters and latent variables, z. Okay. This is exactly what we had going on in LDA. You have observed words, x, for an entire corpus, and then you're trying to jointly infer a distribution, a Bayesian distribution over the topics z, and also the actual parameters for the model, things like theta and phi. And so what we wanted to do was Bayesian inference to estimate the posterior z given x. And again, that was intractable because of the actual model. Okay, so variational inference is going to tackle this problem in a totally different way than what we were doing with MCMC. And it's dramatically more powerful for a lot of reasons, though it also comes with some disadvantages. So let's look at what it does. The idea is to approximate this posterior with some simpler distribution. Okay, so this is the thing that we're trying to estimate, and this is the simpler distribution. And so in general, while we're thinking through variational inference here, I think it's actually better for you to carry problem one as sort of the running example in your mind throughout all of this. And that's actually the one that I'm going to emphasize today. But I want you to kind of have problem two in the back of your mind so that you realize just how sort of general and powerful this method is. Okay. So typically, this simpler distribution, Q of z, is going to have more independence assumptions than P of z given x. And that's going to be fine because Q of z is actually going to be tuned for a specific x. So going back to our homework 2 example, maybe what we could do is, if this is the factor graph for P of z given x, well, we could say that Q of z for that specific x is just going to be the simpler model that you already knew how to do exact inference on, right? The tree structured model. Okay. So if this were the case, well, Q of z has made more independence assumptions. We've left out that linear chain connecting the leaf nodes. But it has a structure that makes everything about it easier to work with. Okay. And so the key idea then is to pick a single distribution, Q of z, from some family that best approximates P of z given x. Okay, so we need some terminology here. Q of z, we're going to call the variational approximation. Okay. And capital Q is going to be the variational family. And we would say that Q of z is going to be some distribution in the variational family. So further, what we're going to do is we're going to work in a setting where, or the typical setting that one would work in, would assume that usually Q of z is parameterized by some vector theta that we call variational parameters. Okay. Likewise, that P of z given x is usually parameterized by some fixed parameters alpha, and we can just kind of refer to them as the parameters like we usually do. Okay. So here, the reason that I like us to focus on problem one is that now we can kind of think of an example of P alpha of z given x would be the actual learned factor graph for some model. Okay, and all you're trying to do is now at test time estimate some distribution for that model. Okay, so we'll come back to the problem of how could you use variational inference to learn alpha. But for now, we can just assume that alpha is fixed, that we have this distribution P of z given x, and we're just trying to do inference with it. Okay, so it turns out that variational inference is really this sort of broad family of algorithms. And the term variational inference actually comes from the term variational methods, which just refer to sort of methods of function approximation by optimization. And so the key property of variational inference algorithms are that they solve the inference problem by boiling it down to some optimization problem, and then using standard optimization techniques to actually do the optimization. So the one that we're going to focus on here is called the mean field approximation. But loopy belief propagation, tree reweighted belief propagation, expectation propagation, they're all other algorithms that are solving inference by optimizing some objective function. It's just that these other three are actually optimizing a different objective function than the one we're going to focus on today. Okay, so yeah.
The function that takes us from x to z, and we're trying to approximate probability of z given x. That function is very simple, just like a linear projection of x into something on some line. Then probability of z given x should be easy to calculate.
So if you're saying if wait, so which what are you saying is actually easy to approximate?
So in your previous slide, there was written that probability of z given x is intractable.
Yes.
But for some functions, it's very simple, right?
Right. And in that case, you don't need variational inference. So what I'm saying here is that the problem is that posterior is intractable. If it's not intractable, then don't use variational inference. Yeah. So for example, on homework 2, we just set it up so that the posterior distribution over the tree was tractable to work with. And so you just ran belief propagation. It was easy. Okay, so now the question becomes, is it trivial to come up with some Q that kind of best approximates P? It's kind of important to notice that we're not defining a new distribution, this simple Q of z given x, but rather we're defining a Q of z for each P of z given x. So Q of z actually doesn't have access to whatever x is. So whatever it is that you're conditioning on, the only reason that Q of z is going to look like P of z given x is because we're going to define some objective function that tries to make them look like each other. Okay, so let's think about like a Markov chain Monte Carlo equivalent of this, right? So suppose you tried to do this with MCMC. Well, you could draw a bunch of samples from, say, the posterior P of z given x, right? Call those z1, z2 up to zn. And then, let's say for that particular x, you train some new model, q theta of z, on those samples. Okay. So when you train that q theta of z, it doesn't know anything about x, But the samples, z1, z2, zn, were sampled from P of z given x, and so they should be representative of the distribution over z's for that particular x. Okay, and so the hope is that that sample kind of adequately represents the posterior for the given x. Okay, so the question is, how is variational inference different from this Markov chain Monte Carlo thing? Well, for one, variational inference does not require sampling. Two, it's going to be usually a lot faster, and it's also going to be deterministic. Then the question is, well, why? So the reason is that we choose some objective function. Okay, the pointer forward is that it's going to be this thing called KL divergence, which we'll talk more about, that defines which Q theta best approximates P alpha. And the fact that it's going to be fast and deterministic is going to be because we'll exploit the sort of special structure of Q theta so that all of this works out to be efficient. So what's really interesting here is that I think this MCMC contrast provides us with is that in variational inference, you have this new design decision in front of you. Okay. Essentially, what variational inference says is, okay, first come up with your model, P alpha. Okay, but choose the model that you really wanted. Don't dumb the model down just so that you can do exact inference on it. Write down the model that you really wanted to work with, the one that you believed in. Okay. Once you've done that, then dumb the model down into something that you can actually work with and call it Q. And then learn a Q that looks kind of like P. Okay, so what are some examples of this? Well, say you had a Markov random field like this one. This is sort of like what you were working with on homework 3 for computer vision, where you have this this pairwise Markov random field, and you have an edge between each pair of adjacent pixels. So we could get back an approximation of that Markov random field simply by removing all of the edge factors. Okay, so what we would be left with are only node factors, or node potentials. And so the Q, so if this was, so let's call this P of z given x, and this over here, Q of z. And then let's just change these x's to z's here. So what we're saying is this approximating distribution is just going to pretend as if it completely factorizes according to the variables. Okay, this is called a mean field approximation. It's what we're actually going to focus on. And what's astounding about this is that we can actually get away with this, and it works really well. Okay, so why on earth would it work? Yeah. Yeah.
So there, that Q theta means that is for each x, like for each input, I'm defining like a different Q theta, or is it like a single distribution which is like income?
Yeah. So for each x, we're going to learn, say, different parameters theta. So we can almost think of like theta is specific to one of our x's.
So will there be like infinite values, like depending on the
Yeah, so the way that you could think about this is suppose suppose you were trying to basically do the test time version of your homework 2, right? So you already have a trained model, and now along comes a test example. That's a new sentence, and you want to produce this like tree of tags for it. Okay, so you're going to run variational inference so that you get back a theta for that new test example. Okay, and at that moment, you will then use that Q theta of z as a way of approximating marginal probabilities for all the output variables.
So I'm leaving with only one sentence.
Yep, exactly. And so in some sense, this MCMC solution mean, it's a straw man solution, right? What I'm saying here is the MCMC solution would take that one test example, run MCMC on it, train some Q theta of Z on those samples, and then completely throw that Q theta of Z and move on to the next test example and start over.
Let me choose the Z which is just the maximizes the probability.
Yeah, so you might choose the Z that maximizes the probability. If you have marginal probabilities for each of your variables, you could do minimum Bayes risk decoding, and if it's Hamming loss, that's just going to be, the most probable assignment to each variable according to its marginal. So once you have the actual distribution over the Z's, there's lots of different things that you could do to actually choose a single Z. Right. Okay, so now maybe this is actually a good moment to pause and think about problem 2 here. Okay, so now suppose X is the entirety of your training data. Okay, well, if X is the entirety of your training data, then Q theta of Z is going to be, say, the distribution over all of the topics for the entire corpus and all of the parameters for, say, a topic model. So that's a totally different, maybe unsupervised way of doing things where you're doing Bayesian inference. Okay, so this is just one example of a way of decomposing things, but there's other ways that you could decompose, right? So for example, you could take little clusters of variables, right? So maybe you take, maybe you don't break it up into individual single variables like this, but rather you say, okay, each collection of 4 random variables, well, we can do exact inference on 4 variables. We can just run variable elimination or something, and it wouldn't be too inefficient. And so maybe our Q distribution actually assumes that each collection of 4 variables is connected. Or maybe, if you're feeling more ambitious, each collection of 16 variables. So we talked briefly about a factorial HMM or a factorial CRF in the context of sort of energy estimation or current estimation. So this is one where you have a bunch of sort of backbones for an HMM, and this is an example where you could just decompose it into a bunch of independent backbones. So this is one backbone, it's not connected in any way to this backbone, which is not connected to this backbone, and so on. Okay. So if you wanted to do this for LDA, there's actually different options available to you. So one would be, you could make that mean field assumption and just remove all the arrows from this graph. And then you could approximate the topics and the parameters with Q. Okay. But you'll remember for the Gibbs sampling that we talked about in class, we actually integrated out theta and phi because of Dirichlet multinomial conjugacy. And we worked with sort of this reduced LDA where alpha went directly to Z and beta went directly to X. So you could actually also work with that model and collapse those parameters out and then just use variational inference to approximate the Z's, for example. And that would give you collapsed variational inference. Okay, so what I want to talk about today is mean field variational inference. And we're going to start with just some background. So what we need first is just a quick look at KL divergence. And I imagine a lot of you have actually seen KL divergence before, but we actually want to make sure that you kind of also understand the behavior of this metric, even if you have sort of seen it written down before. Okay, so the definition of KL divergence is given 2 distributions, Q and P. It's defined to be the expectation under, say, Q of X of the log of Q of X divided by P of X. Okay. So this is the definition for two distributions, Q of x and P of x, for all x in some sort of shared space. So the two distributions have to be distributions over the same output space. So the properties of KL divergence that we care about are that, well, one, the KL of Q and P can be thought of as measuring the proximity of these two distributions, P and Q. So you can think of it like a distance metric, but for probability distributions. Okay. Another important property is that it's not actually symmetric. And so KL of, KL of QP does not equal KL of PQ. The third is that it's minimized when whatever Q of x is equals P of x for all x. So if the two distributions are equal, that's the minimum of the KL divergence. Okay, so what we're going to do in variational inference is try to find a Q of z that best approximates P of z given x according to KL divergence. So what we care about is let's say 3 cases of interest for minimization of KL. So we're going to break these 3 cases up by thinking about, say, the value of Q of x, the value of P of x, and the actual outcome. So the first case is that where Q of x is high and P of x is high. So if both Q of x is high and P of x is high, then is the KL divergence high or low for that particular x? Yeah.
I have a question
Oh,
about
sure.
properties. If the KL divergence of Q and P is minimized, is the KL divergence of P and Q the same then?
Yes. Well, in the so they're minimized when the two distributions are exactly equal. But there's this caveat around whether or not P of x and Q of x can be 0. So let's return to that exact question, but after we get these 3 cases. So think about 0 cases as we're talking about this. Okay, so if both Q of x is high and P of x is high, then is that going to make the KL divergence higher or lower? Lower, right? Because what happens is if Q of x is large, then that means that whatever the term is going to contribute more to that expectation. And if they're both high, then the log of their ratio is going to be the log of, say, something close to 1. And so in that case, the the log of something close to 1 is kind of like 0. So the outcome here is going to be sort of low KL, which in our case is good because this is like a distance metric. Okay, so case number 2, we're going to think about, let me actually write out all 3 cases just so that you sort of see where we're going here. Would be where Q of x is high, P of x is low, and then the third case is going to be where Q of x is low. So, why don't we break it into 4 cases just so you're, when you look back at this, it's not confusing. So this would be high, low. Okay. So, so when Q of x is high and P of x is low, how is that going to affect the KL divergence?
I just had a question, like, what do you mean by high and low? It's not a single point, right? Like the entire distribution. It could be high somewhere, low somewhere.
Yeah. So So
Is it like just for a point?
yes. So let's actually make that explicit. Oops. So basically, what I mean by that is, like, if keeping everything else constant. So keeping all else constant. Consider a particular, say, x prime, and its effect on KL. Thanks for clarifying that. So we'll say, like, there's some specific x prime that we're talking about here. Okay, and we're thinking about how does it affect the KL divergence, keeping everything else the same. Okay, so for that particular x prime, if Q of x prime is high and P of x prime is low, then is this going to relatively sort of push up the KL divergence or push down the KL divergence, or the same?
High.
Yeah, so it's going to be high KL this time. Which, again, for our purposes, if we're trying to minimize, is bad. And why does this happen? Well, if Q of x is high, then again, it makes a big contribution to that integral or sum that is the expectation. And the ratio Q of x px is going to be some positive number, and we just take its log, it's going to be some positive number still. Okay, so the last case is for both of these, because if Q of x prime is low, we don't actually care what P of x prime is, because it basically just doesn't have much effect on KL at all. So we could just say, who cares? Because in this case, it's essentially going to have like no effect. So, okay, so now we come to, so now questions. Yeah, go ahead.
So when we say in property 3 that minimize when Qx equals 3x, and then we say that for all x, so does this, because we are sampling according to Qx, and so there will be some points that will have a high Qx, but there will be some point that will have a low Qx, but might have had a high Px, or Px that is not equal to Qx, but we're not giving importance to that. So in calculating our KL divergence, when we minimize the KL divergence, we will not be giving importance to those points. So for those points, Qx and Px won't be equal, right?
For the points where Q of x was...
Basically, for the points where Q of x is low, it need not be that the KL divergence, basically we have minimized the objective, but it need not be that for those points Qx would be equal to Px, because for that point Qx is low and it had a very low contribution in KL divergence.
Yeah, so that's true, but I guess my statement in property 3 there is that, like, a minimum of KL divergence is achieved when they're equal. So,
Yeah, but what I'm saying is we probably never have a condition where Q of X is equal to Q of X according to the KL divergence definition. Because there will always be some points which will be less important according to Q, over which when we try to optimize, we won't really care about those points.
oh, I guess what I'm saying though is, suppose here, for example, like P is an actual column vector of like 0.7, 0.2, 0.1. And the question is, so this is your distribution P, like that is P of X. And then the question is, what values of the vector Q here for defining a Q of X distribution would give back minimum KL divergence. And so, so what I'm claiming is that, so for example, 1Q would be like 0.1, 0.1, 0.1. Right, so that's like, oh, well, actually that doesn't make sense because we have to sum to 1, right? So if these were, if this was the uniform distribution, like 1/3, 1/3, 1/3, well then we've kind of made them as low as possible, right? But call that Q1. But my claim is that Q2, which is not uniform, so it means that some values of Q actually are high, is actually going to have lower KL divergence. And so I think that the key thing here to remember is that Q is not unconstrained. It's not just a vector. Like we can't have some vector Q that is 0.1, 0.1, 0.1. Like because in that case, we haven't defined a proper probability distribution. And so what's kind of, so this I think is kind of one of the key properties of KL divergence that makes it a little bit different from some other metric that we're used to reasoning with, like Euclidean distance over two vectors, is that we have this constraint on the actual distribution vectors. Another question.
So I was wondering why we consider a particular x, because I thought it was the expectation of the distribution. So shouldn't it be like the mean of the distributions that you use rather than like so the average across like all the x's that you use rather than this particular x?
Yeah. So do you mean well? So hold on. Let's. So if we were to write out this expectation, right? If x was discrete, then it would be a sum over all the x's of q of x log q of x over p of x. If x is discrete, and it would equal an integral over x of q of x log q of x over p of x dx if x is continuous. So I think what you're getting at is
like why are we considering a particular x if it's supposed to be the expectation for all the x's?
oh, down here you mean?
Yeah.
Oh, I guess just because maybe it's harder to, so it's easy to think about like one particular term in that summation. It's harder for me anyway to conceptualize what happens to KL divergence. Like I guess in some sense I don't even know how to like break down the actual like behavior of distributions into cases without boiling it down to like thinking about a particular entry in the actual summation. So that's why I was kind of breaking it down in that way. But you're right that in general what's going on is we have these whole distributions. And so the kind of key thing to think about is that if you, so let's now think about an actual example here. So this is actually maybe example 1. This is example 2. So suppose what you have is some distribution that looks like this, that is Q of x. And it's a two-dimensional Gaussian, mu equal to 0, 0, and a covariance that gets us back this sort of skewed distribution. Okay. And then we define Q of x to be the product of two Gaussians. So it's going to be n1, which gives us a distribution over sort of x1 given mu and sigma squared times n2, which is a distribution over x2 given mu and sigma squared. And let's say these are, specific to the distribution. Okay, so this is actually a mean field approximation. And the question is, what is the Q of x that has lowest KL divergence to P of x for this case? And it turns out that it's going to be a distribution that looks like this, that puts most of its probability mass symmetrically around the origin. Okay, so why on earth would that be the Q of x that we get back here? So Q of x has to be like a symmetrical, let's say, so it doesn't have to be a symmetrical distribution. It could have stretched itself out horizontally or vertically. But if it did that, then, if it looked something like this, say, well then, we have these regions out here and over here, for the green case, where Q of x is high, but P of x is low. And that is going to push the KL divergence up. And so the distribution that it selects is actually going to be like this red one. Okay. So where do we go from here?
Question.
Yeah.
In this case, so the objective is to minimize the KL divergence between P and Q, right?
Uh-huh.
Why didn't it just choose QP?
Why didn't it just choose a diagonal one?
Yeah.
Oh, because I defined Q of x here to be the product of two one-dimensional Gaussians. And so if you take the product of two one-dimensional Gaussians, you can get, you can't get anything diagonal out of it. If you want something that skews diagonally, you need a two-dimensional Gaussian, like P of x, to do that. So maybe I won't go into a deep explanation of that or anything, but yeah, so you can either stretch it horizontally or vertically, but you can't stretch it diagonally.
So that the second property says that KL of Q is not equal to PQ. So to like find whether the two distributions are similar or not, which one to choose? Should I choose Q of P or P of Q?
Great. So let's make one more point here. I wasn't actually planning on making this point, but today we talk about mean field variational inference. Which minimizes KL of Q of z, P of z given x. Okay. And never, not like next lecture, I just don't plan on talking about it. We could talk about expectation propagations. Which instead minimizes KL of P of z given x, Q of z.
So it's not like that if I minimize one, the other one also gets minimized. like they're completely different.
Not necessarily. And the last detail is that both are non-convex optimization problems. Okay. So, I didn't answer your question, did I?
Back to 0.
So I think this example number 2 kind of roughly gives us a sense of the zero case. So imagine what if now we didn't have Gaussians, we had uniform distributions over ellipsoids. Okay, so now we're going to uniformly spread all the probability mass over that diagonal ellipsoid, and that's P of x. And then for Q of x, we can get any ellipsoid so long as it's not diagonal. So you can have a circle, you could stretch it vertically, you could stretch it horizontally, you just can't stretch it diagonally. And the question is, which Q of x would you choose? And here, the answer is going to be one that sort of sits right over top of the black ellipsoid. And that's because what goes horridly wrong is if P of x is 0, then you're going to be taking the log of Q of x, which might be some harmless, 0.001 divided by 0, which maybe if it's not exactly 0, but if it's just close to 0, is going to rocket off to infinity. So that's the thing that we need to be aware of, is that there's this sort of odd behavior, which is that Q of x is going to be sort of placing more probability mass in places that avoid this behavior. Okay. So what does mean field variational inference look like? So today we're going to just outline kind of at a high level what it looks like, and then next time we'll come back and actually sort of derive it. So at a high level, the goal here is to estimate P of z given x. Okay, and we could think about sort of 2 cases of interest. So case 1 is we're given the joint distribution of P of x and z, which means that P of z given x is actually equal to P of x and z divided by P of x. So that's case 1. Case 2 would be we're given, say, a factor graph, which would mean that the conditional distribution P of z given x is something like P tilde of z given x divided by a partition function z of x, where P tilde z given x is just, say, the product of all the potential functions. Okay, so the point is, either way, we have this term in the denominator that we're going to assume to be intractable. So the sort of key point is that P tilde of z given x and the joint P of x and z, both of them need some normalization if you want to work with the posterior P of z given x. Okay. So the idea here is that we want to approximate with another distribution, Q of z, which is going to hopefully be something near P of z given x, for each x. Okay. And let's further incorporate parameters like we did before, so that we have Q of theta and P of alpha. So P alpha. And so mean field variational inference is going to assume that Q theta of z decomposes according to variables. So that would look like a product from t equals 1 to capital T of qt zt, where we have, say, capital T variables here. So you could think of this as decompose over variables. And if we're thinking about this as a factor graph, this looks like z1 with a little factor. That's the qt factor. And then that's the q1 factor. And then z2 has a factor, that's q2. And then all the way up to z capital T, and that has a factor q capital T. Now, it's important to note here that we could actually choose a different decomposition, and other choices for the decomposition of Q give rise to what's called structured mean field. And structured mean field, operationally it kind of works out to be the same, but maybe the computation works out to be a little bit more challenging or something. Okay, so we're going to pick the Q that minimizes KL. And so we can write that sort of one of two ways. One is that we could write, we want some Q hat of z, which is the arg min over distributions Q of z in some family Q. Oops. Where we pick the one that minimizes KL of QZ and P of z given x. Okay. The other way that we could write it is in terms of the parameters, and then we could say we're going to choose some theta hat, which is an arg min over parameter vectors theta that minimizes the KL of Q theta of z and P alpha of z given x. And I actually prefer that we think about it this way, because then what we're saying is the structure of the graphical model for Q is fixed. And all we're doing is trying to figure out what the parameters of the graphical model are that will give us back minimum KL divergence. Okay, so the last question is, how do we actually do the optimization? And what we're going to focus on is optimizing with what's called coordinate descent. And coordinate descent is just a standard algorithm where you pick one dimension at a time to optimize over. And so in our setting, what we're going to do is basically pick the best factor, QT, oops, sure. So we're going to pick the best Q of t zt, and we're going to estimate it conditioned on all the other qt, zt, oops, sorry, qs, zs being fixed for all s not equal to t. So the point is that there's lots of optimization algorithms out there. Stochastic gradient descent, block coordinate descent. We're going to choose coordinate descent, which is going to essentially update the marginal distribution of each variable one at a time. Okay, why are we going to do this? Well, there are other options out there, but this one tends to give us back a really clean-looking algorithm. As well, it's going to give us something that we can draw analogies to Gibbs sampling with. In Gibbs sampling, right, we came up with this full conditional distribution, and then we sampled a value of one variable at a time. Here, that's not what we're doing. We're saying we have these little Q distributions, which are kind of like, distributions over each variable, and maybe unnormalized distributions. And we're essentially saying that we're going to take each one of those, and we're going to estimate the entire distribution for that variable, conditioned on all of the other estimates of those QT distributions. And then we'll pick the next variable, and we'll update its distribution, and the next variable, and so on. And we'll iterate through until we converge. Okay, so we'll look at the details about how important the structure of Q is, and how we can still minimize this efficiently, even if P has a structure that would be really hard to work with. Okay, so that's where we'll pick up on Wednesday. So see you guys then.